All right, this is 13.6 is on the gradient. And so what I'm going to do is I'm going to start with a very simple question. And then we'll define the gradient, and then we'll look at the properties of the gradient. One of them will be that it answers this question, and the other will be that it has other additional properties that sort of go a little further. But the question is this. In 13.5, when we looked at the directional derivative, what we're basically saying is if you choose a direction, if you have a function and you choose a direction, you can figure out the rate of change in that direction, right? So given some, let's say, in 2 dimensions, for example, if we choose a u, let's say a unit vector, then this is the directional derivative. This is the change in f in the direction of u. But what we'd like to do is reverse the question for now. We'd like to say, okay, look, instead of giving a direction and getting a change, can we find the direction in which we get the maximum change, right? So in other words, suppose we want the direction in which the change is maximum. How can we find this direction? This is an interesting question that has lots of actual real-world applications in terms of optimization problems. And so what I'm going to do is I'm going to define the gradient, and then I'm going to prove that the gradient does the things that I claim that it does. So it does a few important things. So given a function, I'll do this in 3 dimensions, but it works equally well in 2. So given a function f of x, y, z, we define the gradient of f. So the notation for this is an upside down triangle. This has a name, I'll tell you in a second. And the definition is I take f sub xi plus f sub yj plus f sub zk. So, a couple things to note. So note A is this symbol is read as nabla. So the notation, this notation can be read as gradient of f or nabla f. So note B is an alternate notation is to just write grad f. There are strengths and weaknesses to both. The nice thing about writing grad is it tells you what you're doing, but the nice thing about writing a nabla is it's sort of instructional in terms of what's actually going on, and we'll say more about that later. And then note C is, keep in mind this is the vector that's resulting. Right, there's an I, j, and a k. And in 2 dimensions there's just an I and a j. But the point is the result is a vector. So, I haven't yet proved that this does anything spectacular, but we'll just do an example. So given a function like f of x, y, z equals x squared y plus z cubed, the gradient of f, I just take the partial derivatives. That's with respect to x, with respect to y, with respect to z. That's the gradient. And then we can plug in points. So if you plug in, say, 1, 3, -2, get a vector, 2 times 1 times 3I plus 1 squared j, oops, I forgot the k up here, plus 3z squared k. So I get a vector. Again, haven't made any claims about it. This is 6I plus 1j plus 12k. So what I'm next going to do is I'm going to make some claims, and then we'll prove those claims. So I'm going to divide the claims into two sets. So I'll call these, let's say, basic claims. And so the first claim I'll make, I'll do by working through a calculation, right? So first observe something. So back in the directional derivative, we saw that the directional derivative in terms of a direction was equal to, right, the original definition was AI plus BJ, sorry, was, that was wrong, was AF sub x plus BF sub y plus CF sub z, which we saw was the same as u dotted with the vector f sub x I plus f sub yj plus f sub zk. That was the last thing we mentioned in 13.5. Now it turns out that this is then the same as u dotted with the gradient, because that vector right there is the gradient. Right? So first note is keep this in mind. Let me put a box around this just so we've noted it. And then let's look at some things that come out of this. So let me clear this left side of the screen and take a look. All right, so from here, remember something about the dot product. So fact about the dot product was that u dot v, just in general, was the magnitude of u times the magnitude of v times the cosine of the angle between them. All right, so that says that the directional derivative is the magnitude of u times the magnitude of the gradient times the cosine of the angle between them. Now, u is a unit vector. Remember, the definition of the directional derivative demanded that the u be a unit vector. So now we know the directional derivative is the magnitude of the gradient times the cosine of the angle between u and the gradient. All right, so here, keep in mind this is where theta is the angle between u and the gradient. So then we ask a question. If I wanted the directional derivative to be as big as possible, how could we do this, right? Well, the gradient is however big it is. So in order to make the directional derivative big, we need to make the cosine big. The biggest the cosine can be is 1, and that occurs when theta is 0. So in other words, thus this directional derivative is maximum when cosine theta equals 1 or when theta equals 0. Now, theta equals 0, that means the angle between u and the gradient is 0, right? So this occurs when u points in the same direction as the gradient. So what this says is that the gradient itself points in the direction of maximum increase or maximum change. Maximum change of f. Furthermore, we can say one more thing, and then we'll look at an example to really clarify. So, furthermore is when the cosine is 1, in other words, when theta is 0, So in addition, so it's sort of a little off the top of the screen. In addition, when theta is 0, the directional derivative will be the magnitude of the gradient. So this gives our final point here in this section, which is that the magnitude of the gradient let's just say we don't need the magnitude there. The magnitude of the gradient equals the maximum directional derivative. So if all this is a bit confusing, that's understandable. What we'll do is we'll look at a very specific example and take a look at what all these things are saying. So let's go back to this example that made a lot of sense for us, which was giving the temperature at a certain point. So suppose this function gives temperature in degrees Celsius at x comma y, with x comma y in meters. So then a bunch of different things we can say. So I haven't asked a question yet, that's okay. Right, let's look at some information. Suppose we're at the point 1, 2. If we plug that into f, we get 1 squared times 2 plus 2 squared is 6. So it's 6 degrees Celsius at 1, 2. So then suppose you're at 1, 2 and you want the temperature to increase as much as possible. Which way do you go? And so at 1, 2, in which direction? Does the temperature increase most rapidly? So the answer is the gradient. So let me spell that correctly. So we take the gradient. So the gradient, in general, gradient of f is 2xyi. That's the derivative with respect to x. Derivative with respect to y is x squared plus 2y. Derivative of f at 1, 2. 2 times 1 times 2 is 4i. Plus x squared plus 2y is 5j. That's the direction. So that's the direction you would go at the point 1, 2 if you wanted the temperature to increase as much as possible. So then you might say, well, how much is it increasing? Well, the answer to that is the magnitude of that. That's the square root of 16 plus 25, which is the square root of 41. So it's increasing at the square root of 41 degrees Celsius per meter. So that's all that information that's stored in the gradient. So again, let me go through one more example where I say this again, but also give like another directional derivative to compare. So let me clear the screen off and sort of run through another similar example. So example, another. So let's do this in terms of, say, height at a certain location. Suppose the height of a mountain at xy. So this is at a horizontal location. It'll give the height. Is, let's say, h of xy equals, say, and we'll do this. This isn't going to be a very high mountain. That's okay. It's 16 minus x squared minus xy. Actually, let's make this x squared y squared. That way it's definitely decreasing as x and y increase. Right? So we could say, let's examine the point, say, 2, 1. So a few things we can say. We can plug it in. So h of 2, 1 is 16 minus 2 squared minus 2 squared times 1 squared. 16 minus 4 is 8. So we're at 8 units. And let's say, let's make this a stupidly tall mountain in miles. Everything will be in miles. So the height is 8 miles. Now it's going to give some weird units, but let's just assume x and y and h are all in miles, and we'll explain the units as we go. So the height at 2, 1 is 8 miles high. So we go, okay, that's great. Now, suppose we're at 2, 1 and we go in a certain direction. So let me pick it, let's suppose we pick a unit vector. Say 1 over root 2 I plus 1 over root 2 j. If we go in this direction, what's the height change? So that's a directional derivative. Right, so we would take the directional derivative of f in that direction. So that's the a times f sub x or h sub x plus the b times the h sub y. So this is 1 over root 2. H sub x is negative 2x minus 2xy squared plus 1 over root 2 derivative with respect to y is negative 2x squared y. So if we plug in our point, get 1 over root 2. Negative 2x is negative 4 minus 2xy squared is negative 4. Negative 2x squared y is negative 4. So we get negative 8 minus 4 is negative 12 over root 2. And this is meters per meter, which is a bit weird, but basically it's meters per meter because we're saying as we move in a horizontal direction, a certain number of meters, we go down a certain number of meters. So it's a bit weird, but it kind of makes sense. So it's a decrease. We're sort of moving away from the peak, we're going down, right? So in this example, so far we gave a direction and we wanted to obtain the change. So let's flip the question around and ask, in what direction is the maximum change? So like back here we had a question, here we have a question. The answer is simply the gradient. So we take the gradient, take derivative with respect to x. So we've done these derivatives before, but here they are. That's the derivative with respect to x, I, plus the derivative with respect to x, or with respect to y, j. Plug in 2, 1. We get the negative 4 again. We get negative 8i minus 4j. So that's the direction of maximum change, right? That direction. And then last question is, what is the maximum change? The answer to that is the magnitude of the gradient, which in this case is the square root of negative 8 squared plus negative 4 squared. That's the square root of 80 meters per meter. That means if we go in the direction given by negative 8i minus 4j will experience an increase of square root of 80 meters per meter, and that's the maximum we could ever encounter. So these last two questions can be summarized as if we go in the direction negative 8i minus 4j, we experience max change, and that max change is the square root of 80 meters per meter. Again, it's instantaneous, it's like a tangent line, but it's saying for every meter we go up by the square root of 80 meters. So those are sort of the basic properties. There's one other property of the gradient that I want to give that I'm going to call a perpendicular property. We'll do an example of that. We'll give that property to an example, mention what it means in 3 dimensions, and then that'll be the end of the section. So let me clear the screen off and do that. So I'm going to call these the perpendicular properties. So I'm going to separate these into two because there's a 2-dimensional version and a 3-dimensional version. So A says the following. Given a function f of xy, the gradient, so we just learned that the gradient points in the direction of maximum increase, but something else is true about it. This is perpendicular to the level curve of f at xy. Now, there's a proof of this in the textbook. I'm not going to go through it. It's not particularly long, but it's a bit technical. But I do want to do an example so we see what this means. So look at the function, say f of xy equals, say, x minus y squared. And let's look at a particular point. Say the point 2, 6. Now, if I plug this in, we get 2 minus 6 squared, which is negative 34. So what this means is that the point 2, 6 is on the level curve of when this is equal to negative 34. Right, that's this level curve. If we take this and we set it equal to negative 34, we get x equals y squared minus 34. This is a particularly icky level curve. Looks like it's a parabola, but it's shifted way to the left. Right, so looks like this. This is down at negative 34. This is x equals y squared minus 34. And the point 2, 6 is right here. That's our point. Now, what this property says is the following. Let's find the gradient of f at 2, 6. So the gradient of f in general is derivative with respect to x, which is 1i minus 2yj at the point of interest. We got 1i minus 12j. So what that tells us is that 1i minus 12j is perpendicular to the level curve. Now, we draw one more picture of this level curve. this point, if we draw that vector, goes 1 unit over and 12 units down. About like that. Notice that is perpendicular. Now, if we stop and we think about this kind of makes sense, because the level curve is the curve on which f doesn't change. So in other words, I'm going to point to my curve with another arrow, which I don't like to do, but there we go. But the point is that on this curve, f is always negative 34. It doesn't matter where you are, because it's the level curve for f equals negative 34. So for example, at the point 2, 6, f is negative 34. F is negative 34 everywhere. So the idea behind the gradient is, look, if you don't want f to change, stay on the level curve. If you want f to change, get off the level curve as quickly as possible, which essentially means going perpendicular to it. So that's what this blue arrow is saying. It's saying, hey, look, I'm perpendicular to the curve. If you follow me, you'll have the biggest possible change. That's what's going on here. So that's the one for a function of 2 variables. So same deal for a function of 3. So let me just put that down here. I'm not going to do an example of that. Oops, let me switch it back to black. But we'll say given. We will do an example of this, but we'll do it. Actually, yeah, let me clear the screen off, do an example of this, because we need this in the next section, so we might as well do an example now so it's fresh in our heads. So B, given a function f of x, y, z, we can say the gradient is perpendicular to the level surface at each point. So let's do one more example. So consider, say, f of x, y, z equals, say, x squared plus y squared. We'll do one that's familiar, minus z. And let's look at the point. Say 2, 3, 10. So note that f of 2, 3, 10 is 2 squared plus 3 squared minus 10. This 13 minus 10 is 3. So 2, 3, 10 is on the level surface. For f of x, y, z equals 3. So this is, if I take that function, f, so equal to 3, we get z equals 3. Actually, let me just write it around. If we, we'll add a z and subtract a 3. So z is x squared plus y squared minus 3. This is a paraboloid opening up with vertex at negative 3. Looks like this. So 2, 3, 10 is sort of 2 units in the x direction, 3 in the y, and 10. So it's sort of up here somewhere. We'll have a better picture in a second. That's a bit ugly. Bear with me. There's x, y, and z. So if we find the gradient of f is 2xi derivative with respect to x, with respect to y, with respect to z. The gradient at our point, 2, 3, 10, is 2x plus 2y minus 1k. So what's happening here is that we have this paraboloid. We have this point that's on it. We have this vector, and this is a bit hard to see because it's a three-dimensional picture. But this vector is perpendicular. It sort of comes out. I'll give it some perspective so you can sort of pretend that it's three-dimensional. Comes out of this paraboloid. It's perpendicular to the paraboloid. To the surface of the paraboloid right there. This is the vector 4i plus 6j minus 1k. It's coming forward and to the right. That's the 4 and the 6. And it's pointing a little bit down. That's the minus 1. This is perpendicular to the paraboloid. And the paraboloid, of course, is the level surface for f equals 3. So we always get something perpendicular to the level curve or to the level surface. So keep that in mind. That last fact about being perpendicular to the level surface will be important for 13.7. So with that, I'm going to end this section.